So welcome everybody to today's webcast from Anybody Technology. My name is Amir Al-Munajed. I'm working for Anybody Technology and I'm the host for today's webcast, and I'm very proud to have Michael Skipper Andersen with me from Aalborg University, and he will give a webcast or a presentation today about patient-specific musculoskeletal model of total knee arthroplasty using force-dependent kinematics. Before we will go to Michael Skipper's presentation, I will give a short who and what is anybody introduction. Then I will hand over the presentation to Michael and he will give his presentation. And then at the end we will have a live questions and answers session where you can have your questions and we will try to answer them live for you. This presentation that Michael is giving today is also part of the GrandChallenge to predict knee forces in vivo, and I think Michael will explain that a little bit more detailed afterwards. So about this webcast today, we will also have a recording of that and we will put that onto YouTube. So if you want to have, if you missed something, you can also have a look later on. And we will also provide a handout of this presentation in form of a PDF and send that around afterwards. If you have any questions, you should see a questions box to the right, like this window that you see here in the middle of the screen, and you can type in your questions here all the time. So whenever you have a question, please feel free to enter that in here, and so either at the end Michael and I will try to answer those questions immediately live for you, or some of my colleagues will answer those questions in this question box, so as a private chat message to you back. So very briefly, who is Anybody? So there's a company called Anybody Technology. That's where I'm working. We provide the Anybody modeling system, so the software, the licenses, we give training, we give support on that, and we also do consulting projects regarding the Anybody modeling system. We are placed in Aalborg, Denmark, and we have also an office in Boston, the US. Aalborg Anybody Technology is a spin-off company out of Aalborg University, and this is where our main research group is located. So the one in Aalborg University around Professor Rasmussen, that's doing mostly biomechanics, orthopedics, ergonomics, sport and automotive research. And this is also where Michael Skipper Andersen, the presenter from today, is based. We also have another research group in the US at the Colorado School of Mines with Professor Patella, and another one in Germany at the OTH Regensburg, that's Professor Sebastian Dehndorfer. And we have several resellers all around the world that provide the Anybody modeling system for us. So Anybody, when we talk about Anybody as a software, there are two different products. One is what we call the AMS, the Anybody modeling system, which is the software itself. In this software you can load a model, run a model and analyze or do a musculoskeletal simulation. And all those models, you get what we call AMMR, you get an Anybody managed model repository with the modeling system. In there's the full information to have a body model, a human body model, and there's a library of applications. So you will have initially several applications like a subject cycling a bike, or some sport applications, or some gait, or some orthopedic applications in there. And you can analyze either those or then adjust those models to your own idea or to your own project. So musculoskeletal simulation in Anybody means as input we need an activity, so a motion. So motion is input. We have a body model containing bones, joints, muscles and ligaments, and then as output you get the internal forces of the muscles, muscle activity, power, and also for the joints you get forces, moments. And you could also get interaction forces between the subject and the environment. So this principle is called inverse dynamics. Once again, on the left side input is motion and external forces. The output is muscle forces, joint reactions, so everything what's going on inside the human body. On the right-hand side, you see a screenshot of the full human body model with some details like the detailed shoulder, the lumbar spine, hip region, knee, and the foot model that's in the software. So typically, the Anybody modeling system is used in many different areas. So if you start on the top, product design optimization, so you can optimize, let's say, a wheelchair to get the optimal position for the subject in there to have the lowest shoulder forces, or you can analyze do an ergonomic analysis and documentation in regards to automotive or all kind of products. You can do surgical planning, evaluation, and failure analysis. This is more related to what we hear later on from Michael. Then you can export physiological load cases into finite element analysis, and you can also process gait trials in the gait application called AnyGait. So typically you would have an application like an activity of daily living and analyze that in Anybody to compute muscle activities, forces, or joint forces and moments. You can also fully adapt this human body model. So for example, if you have subject information from MRI or from CT, from Materialise, for example, from mimics, then you can use that information to make a subject-specific model, and then you can output everything into FE. And even more, there are more interfaces. So if you have an environment designed in, for example, in CAD, in SolidWorks, there's a translator from SolidWorks to Anybody to hook up a complex environment, like in here, sports equipment, so an elliptical trainer with the body model. And you can do also some advanced, hook it up with some advanced scripting languages like Python or some optimization softwares. So that's enough about the general introduction. So now we will have Michael Skipper Andersen. He did a Master of Science in Control Engineering at Aalborg University, and afterwards he made his PhD in Biomechanics in Aalborg University. And since 2009 he's employed at Aalborg University, first as an assistant professor, and now since 2012 as an associate professor at the Department of Mechanical and Manufacturing Engineering in the Faculty of Engineering and Science. And today he will talk about patient-specific musculoskeletal modeling of total knee arthroplasty using force-dependent kinematics. So I will hand over the presentation to Michael, and I wish you good luck with your presentation.
Thank you very much, Amir. I'll just wait for my slides to come up. They should be in just a second. But while we wait, I would like to first there we go. I think we should be on the air now. So first of all, I'd like to acknowledge all my co-authors, because this project that we did would not have been possible without them. So it's Marra from Radbound in the Netherlands, Valentine Vanheule from Belgium, from Materialise in Belgium, Rene Fluit from University of Twente, Nico Verdonschot, also from Radbound University Medical Center in the Netherlands, and John Rasmussen from our group. And what I'm going to present to you today is our entry into the GrandChallenge competition. I will explain in a bit what that is, and actually the competition we won this year. So as Amir already told me, or already told us, is why we do musculoskeletal modeling. So that's because we want to estimate something we cannot measure, typically in a normal setting. So examples are here on the right. For instance, a guy lifting a box. We can typically not, on normal subjects, measure the forces within the spine. There might be situations where we can, but typically we cannot. So if we want to gain insight into what is going on inside the body, we need to estimate them somehow. The same is the case for total knee arthroplasty, where a typical implant cannot measure the forces that are actually affecting that particular implant in view. There are again some situations where they might be available, as I will show you later, or an example more with an elliptical machine. So basically what we want to do is estimate something we cannot measure, to get some insight into what is going on in the body. And these could be muscle loads, joint loads, bone loads, ligament loads, or even joint movements, as I'll show you later. So if you want to apply this for clinical applications, so in that particular case, we need to be able to make patient-specific models because we want to exactly do the intervention on some particular patient with some particular problem. However, also, if we want to do that, it's very, very critical that our models are valid. So if we want to do predictions for patients, we want to make sure that the models are actually valid so that we don't make wrong judgments in the clinics. So the GrandChallenge is a very good and unique opportunity to do blind model validation. It's organized by PJ Frackley and Daryl DeLima and for Beshier, and all the information about it you can find on the simtk.org website. If you search for knee loads, you can find all the data, all the explanation of the competition. I'll just give you a brief introduction to what it's all about. So the idea is that they wanted to challenge the musculoskeletal community to actually critically validate their predictions that they've been doing for forces within the knee. So they developed a knee that can measure the contact forces, actually all 6 force and moment components in the knee, and implanted this into patients. They've been doing this. This year was the 5th competition. There's one more next year. It's actually just started, but with end day next year. So if anyone want to participate in that one, I warmly recommend that you go to the site and find the data. So the idea is that they measure the contact forces doing typically 2 different activities that is for the competition. One is gait, and then the other one is another activity. For the 2014 competition, it was a right turn, so the guy was stepping to the right. And then they released all the normal data on this subject in the lab, so they measured marker trajectories, ground reaction forces. They also did CT, pre and post-op of the leg, so from hip to the ankle, EMG, and also some fluoroscopy trials, and also a bit more data, but I will not get into that. But they did not release the measured contact force in the knee. So then they first asked people to blindly predict the forces in the knee. So that was first part of it, do blind prediction of the knee forces. And then after that, when everyone had submitted their results, they released the force data, and then people were instructed to make unblinded predictions. And as I said, this year it was for gait and for a right turn. So there were kind of 2 tempi. We have blinded results and then unblinded results. And I'll try to explain what we did in between those 2 to get from our blinded results to get some even better unblinded results. So what did we do? So how did we go about this? I'll try to give an overview over our whole modeling setup. It's a little too involved to go into all the details, but I'll try to give an overview of what we did. So we started with segmentation of the pre-op bones from CT here, and we did this in mimics. The next one, we wanted to construct both complete bones from the patient pre-op, and we also needed complete bones post-op of the patient, and we also wanted them registered to each other. So that's what we did in the next step. So we created complete bones for the pre-op and for the post-op and registered them to each other. Once we had done that, we used the pre-op bone, so the patient before surgery, the bones of him, to actually nonlinearly scale our musculoskeletal model. And it's based on this new TLIM dataset, version 2.0, which was a publication out by Fluit, and I think that's just a conference abstract for now, but I think there's a journal paper on its way. So the idea is that the gray bone that you see here in the middle, that is the patient-specific bone, and what is it? It's bluish one that you can see in the background is the TLIM generic bone. So then what we did was that we took and stretched no, sorry, it's the other way around. The gray one is the TLIM bone, and the blue one is the patient-specific bone. So we took the bone from the TLIM model and then stretched that until it was the same shape as the patient bone. And then what we did was that we interpolated over the entire surface to create a nonlinear mapping, so that all the muscle insertions that were defined on the TLIM cadaver bone were also morphed to the right locations on the patient bone. because we don't have any information on the muscles in the dataset because it's only CT. And we did this for all the bones that were available in the datasets, which were the femur, the tibia, patella, fibula, and part of talus. There's no scan of the foot, and there's no complete scan of pelvis as well. So actually over here you see the bones that were actually available, so only for the affected leg, and then complete scans from the hip and down to the ankle, and then part of talus and part of the calcaneus. So next step we did was that we fitted analytical surfaces. So we tried to identify the hip joint center with a spherical fit to the hip. We also tried to find the axis of the tibiofemoral joint and the patellofemoral joint by doing cylinder fits to the implant, as you can see here. And actually this particular implant is very circular, so actually a cylindrical fit is actually a very good fit. For the ankle, we fitted 2 spheres to the talus, to the top part of the talus, and then found the ankle axis as the line connecting the 2 origins. So then as I said, we only had some bones. So to make a complete model, we also need to scale the rest. So for instance, the unaffected leg, we had to scale somehow, and also the upper body and the feet. And the idea here was that we assumed that the patient was symmetric, so for all the bones that we had, we mirrored them from the left to the right. For pelvis and the feet and upper body, we don't have any information from the scans. So what we did was that we placed the markers that were recorded in a standing reference trial on the bony landmarks where we thought they were, according to the marker protocol. And then we scaled the model so that it fit in the standing reference trial. So we scaled the pelvis width and the feet length until he matched in this particular standing reference trial. Once we have done that, we still assumed idealized joints. So we actually put in a revolute joint at the knee for now, and then we tracked the markers. So we tracked the marker trajectories for the 2 trials. So on the left here, you have the gait trial. So he's tracking the markers for the gait trial. And also on the right, you see the step to the right on his affected left leg. And then from this model, we saved all the joint angles. So all the generalized coordinates for this one here, and we're going to use that in a bit. Then we went to do a detailed model of the joint. Actually, you can see it here. We actually introduced both contacts between the components of the total knee replacement, and we also introduced ligaments as well as we could. And then we used a method called force-dependent kinematics to actually resolve both the internal forces and also movement within the joint, and also muscle forces and so on. But I'll explain that in the next slide, how we did this. And then finally, we had some results, which would be the medial contact force and the lateral contact force that we're looking at. Well, I'll come back to that. But that's basically the overview. So we started from images to full detailed modeling of the knee. So what is force-dependent kinematics? It was developed by me and Michael Damsgaard here at Univeristy Technology. So the idea is that we want to simultaneously compute muscle forces, joint forces, ligament forces, and internal joint kinematics. So we don't want to put in a revolute joint within the knee, but instead we want to have it stabilized by the soft tissues around the knee. So the ligaments and all the external loads and muscle forces should determine what the internal movements of the joint is. And the idea here is that we basically wrap a solver around inverse dynamics, where it controls some degrees of freedom. These we call FDK positions. I'll come back to what they are for this particular setup. And then once you have positioned these degrees of freedom, you can then compute what the forces would be to create static equilibrium with this position. If you don't position everything where all the ligaments are in balance and all the forces are in balance, you of course end up with residual forces. So those we then take out, and then we make a nonlinear solver search for the positions in the FDK positions here that gives no reaction forces. So we basically search for static equilibrium within these degrees of freedom. Yeah, and for muscle recruitment, we used a quite commonly used one, so the sum of muscle activities cubed within the inverse dynamics. So the degrees of freedom of the patellofemoral joint and the tibiofemoral joint, that was that we drove the flexion angle, so the flexion angle that we had out from the dynamic trial from the marker tracking, that we used as input so that the flexion angle is like that. We assumed that the patella tendon was rigid. It's actually indicated here in red. So we assumed that the patella tendon is rigid. And then the remaining degrees of freedom of these joints, which there are 10 left, so internal, external rotation, abduction, anterior, posterior translations, and so on. All of those we search for static equilibrium between all the applied forces. So ligaments, contact, and so on. As contact model, we used a rigid contact model, which is based on the volume penetration of STL surfaces. So we have all the STL surfaces from the components, and then we compute an overlapping volume to generate the contact forces. And we included all the major ligaments around the knee, and all of them were modeled with kind of standard nonlinear elastic springs with wrapping surfaces. Then there's strength scaling. What we normally do in our models is that we use this, what we call length, mass, fat scaling, which is based on the segment length, masses, and also the subject's height, which from mass and height you can estimate the BMI. And this was published by John Rasmussen in 2005. However, if you look at these total knee patients, it has been reported actually a few times that they have reduced knee flexor and extensor strength after the surgery. There's this paper here. I just took one example where they have reported an average isometric flexion strength reduction of 32%, and also an isometric average isometric extension strength of 31%. However, if you look at the around full extension, the reduction is actually even higher, up to 40%. And since the data set did actually not include any strength measurements, well, there's actually a problem in the data, so we couldn't use it. So we didn't have any strength measurement on the subject. So what we did was that we reduced all the strength of all knee flexors and extensors by 35%, which is kind of in the middle of what has been reported in this paper. Ideally, we should have had patient-specific strength. So what did we then get for our blinded results? So these were submitted in January 2014, so here early in the year, and the data was released in September last year, so that was after around 4 months after the release date. So what did we get? So again, we have these two trials, a gait trial, normal standard gait, and we have this right turn, where you're stepping on a platform and then going to the right. So the blinded results, let's take the right turn first. So what we have here in the top row is that we have the medial contact force as a function of the gait cycle on the left. We have the lateral contact force as a function of the gait cycle in the middle, and then the total contact force as a function of the gait cycle on the right. The model is black, and the experimental data is red. Actually, we have a, I think, very good match here. We have for the medial force under prediction all the way through stance. We have a slight over prediction at toe off for the lateral force, here around 55% or just before 60% of gait cycle. And then we also, in general, a little bit under on the total contact force. But in general, we're very good, and the total contact force has a RMS error of less than 200 Newton and an R squared of 93. So then what about gait? Actually, I would like to start on the right. If you look at the total contact force, it follows very nicely until the second peak, where it actually kind of significantly over-predicts the second peak, but follows very nicely the rest of the way. If you look at the medial force on the left, it also has the first 50%, approximately 45% of stance. It also follows the measured force very, very well, and then it over-predicts the second peak. The lateral force has the right trend. It has a peak between 0 and 20%, and a peak between 40 and 60%, and again one just before a heel strike again. So it has the right trend. So the task was that from our blinded predictions to our unblinded prediction, we had to figure out where did this second peak over a prediction come from, and is there, a fundamental thing that we're doing in the model that explains this, and what is the solution? Yeah, so once everyone had submitted all the blinded results, all the knee contact forces were released, so the measured ones. That was in February this year. And then we had some time to actually do model improvements and figure out especially where this second peak came from. So if we go back, and this is the most important thing that we had to change to get the forces correct, and I think this is a very fundamental issue in this particular model. So if you look at the way Klein-Horstmann in the original dataset of the T-limb dataset discretized the muscles, the soleus and the gastrocnemius. Then in soleus, he made the medialis into 3 branches because it has a large insertion area, and also for lateralis, he split that into 3 branches, each having a third of the total isometric strength. Gastrocnemius, that was modeled as 1 branch each. So if you look at this from take 1 branch of the soleus medialis, then that is from a muscle recruitment point of view a smaller muscle than gastrocnemius. And as Joachim Holmberg and Klabring showed a few years ago, is that the muscle recruitment criteria that we actually have here, and it's actually very frequently used, they're sensitive to how you actually discretize the muscle. And actually the form that you have here on the right, where you have the muscle activities to some power, and when the power is low, it's going to pick out the larger muscles. So this means that because the soleus now is split into 3 and gastrocnemius is split into 1, the recruitment will actually favor activating the gastrocnemius, which is a biarticular muscle, which will then also affect the knee. And if you look at their activations, then they're actually activated at the same time as this second peak. So having the ratio between the 2 off will largely affect what is going on at the knee. And of course, what is not so nice here is that if we had now split the soleus into 4 branches, that might have been reasonable to do, then we would have gotten an even larger overprediction at the knee, whereas if we had only split it into 1, that would have reduced it. So we should come up with a way to actually reduce this dependency on the criteria. So we went back, and there's actually an idea on, not specifically on how to handle this issue with splitting muscles, but there's actually recruitment criteria that was proposed by Happy and Vanheule already back in 1995, which I think actually solves this problem, and I think it has some nice properties as well. So the idea is that instead of saying that it's the cost of activating a muscle, then it's the cost of activating a muscle volume element that we have with this activity to a power. And then the total cost we obtain by doing a sum over all the volumes. So basically what this means is that we should introduce a volume weight in front of all the components here in our muscle recruitment problem. The volume we then try to estimate as the physiological cross-sectional area times the optimal fiber length, which was the information we had. We could also have used MRI if it had been available to estimate muscle volumes, put those in, but that was not available. So then when a muscle then was split into, for instance, 3 branches or 4 branches, each branch then gets a fraction of the total volume of that muscle. So for soleus, each of the branches would have a third of the volume of the muscle, and so on. And this will then actually eliminate this whole issue of muscle splitting. We also did some other minor things, which I don't think are as important as the recruitment, as you'll see in a bit. But one thing we did was we went back and looked at if you had placed the markers the right place on the model. And for pelvis, it was actually particularly tricky because we didn't have a full CT. And also, if you look at this particular subject, he actually has quite a bit of abdominal fat. So the question is, where is the pelvic bone inside this when you see the markers? And in the beginning, we had placed the bone kind of in the middle. So we had assumed that the this offset was on both sides, so it's completely symmetric. But this is probably not true for this patient, so we moved pelvis back a bit so that it had more more of an offset towards the anterior side. In the beginning, we had also estimated the patella tendon length from the CT images, but as I will also show in a bit, we actually segmented the fluoroscopy trials as well. So there we thought we had a better estimate of the length of the patella tendon from the fluoroscopy, so we used that one instead. So we estimated the length of the patella tendon from a fluoroscopy trial instead. And then last but not least, we tried to improve the modeling of the ligaments. So especially we put in more wrapping surfaces, so the wrapping around the femoral condyle and the component for the ligaments that have to do with the patella. And also we improved the wrapping of the PCL around the component. So then we submitted our unblinded results, which were submitted in June this year. So what did we then get? Again, let's start with the right turn, with this new criteria and these smaller updates. If you look at the medial contact force again, it's still underpredicted, actually a little bit more underpredicted than it was before. The lateral force is actually better. It's still a little bit over around toe off, but not very much. And then generally, for the total contact force, it's underpredicted all the way through stance a little bit, but no substantial change here. What happened then for gait is that if you start again with the total contact force on the right, then this large overprediction of the second peak is now gone. So we have actually slightly underprediction all the way through stance, and then a little bit of overprediction at toe off. But I actually like the fact that now we are underpredicting, because we know that these models here have an underestimation of very likely an underestimation of the muscle co-contraction, and now there's actually room for improving that in the predictions as well. If you look at the medial contact force, that's actually not too far off. It's there's a little bit here around toe off again, where the estimated force is kind of delayed compared to the measured force, but amplitude-wise it looks okay. The lateral contact force is underpredicted all the way. It has all the right peaks, but it has slightly underpredicted all the way. But I think in general, for something that is a biological system, this is actually very good. Okay, so then as I said, they also had fluoroscopy, and as I also mentioned, that this FDK method actually not only estimates the forces in the joint, but also the kinematics. So fluoroscopy actually offers a chance of also validating which movements are actually going on inside the joint. So what we did was that we took one of the unloaded fluoroscopy trials that you see up here on the left, and then we wrote a bit of MATLAB code to actually segment the different components out. You should actually be able to see it up here on the right-hand side. So now it's tracking the anterior part of the component, and it will start over in just a second. So we track patella, as you can see up here on the right. So we track the contour of patella and estimated the edge of the implant. We also track the tip of the femoral component in the image. We tracked an edge of the femoral component, and then we, as we saw already, we also No? Did we lose sound? Okay, sorry about that. I guess we lost sound for just a second. Yeah, so what we did was we then recreated the movement from the fluoroscopy. So we made a model that had the same knee flexion angle as in the fluoroscopy, and then computed all the movements that actually happened within the joint, so that we can compare directly with those we had in the fluoroscopy. So just to repeat, the things we tracked was this tip of the femoral component. We tracked the edge that's in this image vertical, or if it's full extension, the anterior part of the femoral component. We also track the frame on the patella, which has an axis aligned with the edge of the patella component. And then we attach the femoral frame here to the anterior part of the tibial tray. Okay, so what did we then get? So on the left side here, we have the flexion ankle between patella and femur. So if we look down in the little image here, so that's between the green line here and the blue line. So that's the ankle between those two. And we did this for both the fluoroscopy, which is the gray line, and FDK, which is blue. And then we also put in the Revolute joint model that we had from these analytical fits. What would we actually get if we had put in a Revolute joint? If we look at the FDK patella flexion ankle here, as a function of knee flexion ankle, we actually have a very good fit in terms of the patella flexion. It deviates a bit, around 65, something like that, knee flexion ankle. The Revolute joint based model is actually offset, so it has a higher patellofemoral flexion ankle than measured in vivo. If we look at the tip shift, then this is the two other pictures, the distal proximal tip shift and the posterior anterior tip shift. And again, we actually see a very good estimation from the FTK model, both in distal proximal shift and also in the posterior anterior shift as a function of knee flexion ankle. The Revolute joint model is actually not too bad for this particular implant, except when we get up into 90-degree flexion or even more, then it starts deviating more and more. But the FTK model actually follows it quite nicely throughout the entire range of motion. Okay, so what did we learn from this exercise? So we saw that we got good knee forces and also secondary, of course, only planar kinematics in this particular case because we only had single plane fluoroscopy. We also saw that the computed forces are sensitive to the muscle decomposition, as also reported by Klarbring and Holberg, and this is with the typical recruitment criterion. Then when we introduce these muscle weights, so the volume, the weight that is the volume of the muscle in the prediction, we actually got much better prediction both of for both trials. And of course we saw that we could generate a patient-specific model, but it was not easy to do, so we need more work there in terms of automating this process. Yeah, so future work, automate the whole process of doing patient-specific modeling, which we need if we want to apply something like this in clinics. For the ligaments, as they didn't do any laxity tests on the subjects, we just adopted values from the literature, and again in clinics we would need patient-specific ligament properties, so assessment of that. Also for these patients we need patient-specific strength scaling. Right now we just took the average reported reduction in knee flexor and extensor strength, but this might not be true for this particular patient. We also need to improve the prediction of co-contraction, which we saw for both trials now. We underpredicted the total force, so this leaves room for actually putting in some more prediction of co-contraction. And then of course, last but not least, we should apply the model to real problems. So with that, I would like to thank you for your attention and hand the word back to Emir.
Okay, Michael, thank you very much for this presentation. It seems like you have done an impressive study there. I also want to thank at that point to BJ Fragley, Daryl DeLima and Tor Bézier for organizing this GrandChallenge competition. I think it's a very good opportunity for all of us in the field of musculoskeletal simulation to create advanced models, but also to validate them. And I think that's the most important point here. And we have seen with those really good results that Michael showed here that we are very close to a clinical application of those models. And by that I also want to thank Michael and all the co-workers for winning this challenge in this competition in 2014. So yeah, I want to thank Michael again for this presentation and for all of you out there. So we have answered quite some questions in the meantime. Please feel free to enter more questions in the questions box that you see to your side. You might have to open this orange arrow and then it will unfold. There are many ways to get in contact with anybody. There's of course the homepage anybodytech.com, where also this webcast is going to be put up there. You will see a list of events, dates, publications there. We have a community homepage called anyscript.org with a wiki and a forum and a YouTube channel. We will have another webcast in 3 weeks from now, where Tim Weber from the biomechanics lab of the OTH Regensburg will give a presentation about the biomechanical outcome of total hip replacements using also a patient-specific musculoskeletal model. We are also present at several other conferences. So my colleague will be in Leipzig in 2 weeks at the Mimics Innovation course and will show something about the interaction of anybody and mimics. I will be in October at the Human Modeling and Simulation and Automotive Engineering conference in Munich, Germany, and we will also be at the BMES meeting in San Antonio, Texas in late October. There's also a course on musculoskeletal simulation in Regensburg in 2 weeks from now. I'm told it's full, but we have to see if there are some spaces left.